Hello guys, good evening everyone. How are you? Okay guys, so where were we in the last class? Could you tell me? Just a second, we'll start. 2 minutes. Okay, so I think we had discussed Heisenberg uncertainty principle, correct? Yeah, and questions also we have discussed on that. Okay, so Heisenberg principle suggests that we cannot find out the exact position and momentum of an electron. Okay. Right. And this was the big blow for Bohr's atomic model, because unlike Heisenberg, he was suggesting that we had the exact position of an electron. It resides in an orbit which has a fixed distance from the nucleus, and in that orbit it has a fixed kinetic energy, potential energy, and its velocity. Correct? So according to Bohr's, we know the exact position and velocity of electrons, but Heisenberg said the opposite of it, right? The statement given by Heisenberg, it is a contradictory statement to the statement of Bohr's model. Okay, that's why we discarded Bohr's model also later on. Okay, it was not completely wrong, but yes, it was not 100% correct also. Few things was not correct in Bohr's model. That's why we discarded Bohr's model later on, right? So after this, Heisenberg, a wave mechanical model based on the quantum mechanics developed by the scientist, mainly Schrodinger. Okay, and based on that, we talk about the presence of electron, where the electron presents, what is the exact thing within an atom in which the electron is present. We get all those ideas, right? That is based on quantum mechanics, right? That is wave mechanical model. Okay, so this, obviously the quantum mechanics, we won't be able to understand it properly at this level. So we'll just take few reference of it. Okay, we won't go into depth of it. We'll take few reference of it to understand the Schrodinger equation. Okay, right. So one statement first you write down, and then we'll move on to it. Write down the statement. When Heisenberg uncertainty principle I'll also write down it. Just a second. The statement is, when Heisenberg based on the data given oral, you can easily find out. Yes, with practice you will have the idea of it, that which formula we should use. But based on the data given, you can understand. Okay. So write down this particular statement here. When Heisenberg uncertainty principle came into existence, or came into picture, the concept of electron revolving around the nucleus in different orbit where the position and velocity are exactly known was replaced by the probability of finding an electron in a particular space or volume. Right? So after Heisenberg, we said that the concept that we get is, this is an orbit, suppose we have, and this is a volume, right? A three-dimensional space or volume. So initially Bohr suggested that electron revolves in a fixed path called orbit, circular path called orbit. This is a nucleus here. So this is orbit, right? Since Heisenberg suggests that the exact position and momentum we cannot find out. So fine, we said what? Okay, we cannot pinpoint the location of electron, but we can say, okay, the electron present in this region. In this region, definitely the electron is present, right? So the certainty here, it converts into probability. After this Heisenberg, we started talking about the probability of finding an electron. We don't talk about certainty now, but we started talking about the probability of finding an electron, right? So this is the three-dimensional space. And in this space, we can say the probability of finding an electron is maximum, correct? So this was the biggest, achievement of this particular theory. We are not talking about a pinpoint location of an electron, but we are talking about a volume in which the probability of finding an electron is maximum. Okay. So what is this? This is three-dimensional space or volume. 3D space. After this concept only, the entire thing, we got to know about a new concept, and this concept we call it as orbital, right? So after this only, like I told you in the beginning, there's nothing called orbit within an atom. The thing is orbital, not orbit. The concept of orbit was vanished after this, and we started talking about orbital, BITAL, orbital, right? So write down the statement here, just one line we have. It is a three-dimensional space. Orbital, write down, it is a three-dimensional space orbital, write down, it is a three-dimensional space where the probability of finding an electron is maximum. Three-dimensional space where the probability of finding an electron is maximum. Right, so this is what orbital. So after this, we won't talk about orbit. Orbit is nothing, like it won't exist. The correct thing is orbital, right? So this thing we came to know when we got to know the wave characteristics of electron from de Broglie wavelength, right? That all microscopic particles, when in motion, contains wave characteristics. And when we study these wave characteristics, we'll get to know about all these things, correct? So this is, after this only, a new model has been developed, given by the scientist, mainly Schrodinger, okay, but the research and study was done by Heisenberg and Schrodinger both, right? And this we call it as quantum mechanical model of an atom. Write down. Quantum mechanical model. Okay, so what is quantum mechanical model? Write down. It is based on the quantum mechanics. It is based on quantum mechanics. See, there are basically two things. One is classical mechanics, other one is quantum mechanics. Classical mechanics, where we have the Newton's laws of motion, and all these things are valid, right? On macroscopic objects, like any object, we apply Newton's laws of motion. But when it comes to microscopic objects like electron, which contains both particle as well as wave characteristics. Okay, so the particles which has dual nature, For those kind of particles, the classical mechanics fails. It is not valid, right? Don't give you correct result. Classical mechanics. Newton's laws of motion, we don't apply into that, right? Basically, Newton's laws of motion, that is classical mechanics, is applied for macroscopic particles, not for micro, okay, for macroscopic particles. So for microscopic particles, we have quantum mechanics. We used to understand their behavior properties with the help of quantum mechanics. Write down next line. Right, the quantum mechanics, it is based on quantum mechanics. Next, write down. Quantum mechanics is a theoretical science Quantum mechanics is the theoretical science that deals with the study of the motion of microscopic objects right? The theoretical science that deals with the study of the motions of microscopic particles, which has both, or write down, which has dual characteristics. Okay, which deals with the study of the motion of the microscopic objects, which has both characteristics. Both characteristics means wave and particle nature. Okay, next time you write down. It is developed by Heisenberg and Schrodinger. It is developed by Heisenberg and Schrodinger. Heisenberg and Schrodinger. Now you see what happens here. Schrodinger actually, he defines a new function here. To understand this behavior, he defines a new function that is psi, represented by this line. It's kind of Trishul, if you have seen Lord Shiva. Okay, similar kind of term we have here, right? This we call it as this kind of this. Okay, this is psi. This is psi. The term we call it as psi. Okay, so Schrodinger has given this term, and this term is called the wave function. Wave function or amplitude function. Amplitude function. Wave function or amplitude function. Correct? Okay. This, you can compare this with the amplitude of any wave, any light wave. Like light wave has some amplitude, any wave has some amplitude. So this is the amplitude of electron wave, you can say. It is the term he defined for the waves associated with electron. Correct? And hence we call it as the amplitude of, actually it is the amplitude of electron wave. Electron wave. Okay. So light wave, for example, you see, for example, if you have light wave has amplitude A, suppose, has amplitude A. Suppose, I'm assuming this, right? Then what we say, the intensity of light wave I is directly proportional to a square, the square of the amplitude, right? Similarly, if you have an electron wave, with amplitude psi, okay, so intensity of electron wave is also directly proportional to psi square. Okay, I'm discussing these things here, but you won't get question on this. Okay, I'm just discussing to you for you to have an idea of it. Nothing much, required here. Intensity is psi square. Since this represents the amplitude function or wave function of an electron, and intensity is directly proportional to psi square, this means what? Psi square is what? Psi square represents the intensity of electrons. Psi square represents intensity of electron. If you have more value of psi square, more will be the intensity of electron and more will be the probability to get an electron, right? That's why psi square, we also call it as probability per unit volume. Probability per unit volume. This also we call it as probability density function. Probability density function. So this is what you should understand. What is psi? Psi is the wave function or amplitude function. But psi square is the probability density function. Density means per unit volume calculation we are doing. Charge density means charge per unit volume. Similarly, probability density means probability per unit volume. Correct? So these are the two terms given by them. Okay. Now, with the help of this wave function, one more thing, this wave function actually, it consists of all informations of electron. Okay. It consists of all information for an electron. So if you want to get some information about electron, you should take wave function of that particular electron and you should study the wave function. That is it. It gives you all the properties of electron, like its energy and other things, right? Okay, one point is this. Another point, it is probability per unit volume. So suppose we have psi square is probability per unit volume. Suppose we have a volume, a very small volume we are considering, right? This is the volume and the volume is three-dimensional thing, right? So if very small volume we assume, that is dx into dy into dz. This is a very small volume we have. We are considering this, right? Very small volume. So psi square is equals to, we have already seen, it is probability per unit volume. Okay, so probability, if you find out from this equation, probability is equals to psi square into volume, and that would be psi square into dx, dy and dz. This is the probability. So if you integrate this 3 times, because we have 3 terms, dx, dy and dz, psi square dx, dy, dz, this gives you the probability of an electron in this particular volume. in this particular volume. Okay. So maximum probability is 1. So probability of getting an electron is triple integration of this psi square dx dy dz is equals to 1. The maximum probability is this. Okay, this is the thing here. Now, for different volume, you don't have to solve this. Triple integration is not there in your textbook, right? So for different volume, we have different value of psi also. Is it Kshitish? Acha, we'll quickly then. I forgot. You did not tell me. Anyways, could you tell me what is the last portion I discussed? Acha, we did Hansul. Okay. Fine. So that's why I was thinking that you are not asking any doubt. Okay. Anyways, so guys, we have done it already, no? Anyways. Okay, fine. I got it. It means we have done all those things, quantum number, other things we have done, right? Achha, fine. No problem. Just you will. Okay, fine. You had a revision of it. Fine. So actually, okay. Electronic configuration we have done. Hansul we have done. Okay, nodal surface we need to do. Correct. Okay, one last thing we'll see. See, this equation actually, it has two components. I'll tell you what it is. This equation has two components. I'm just leaving all these things now. Psi actually has two components. When you solve this, I'm doing this, for you just to, because one question they ask into this, a pattern is there. I'll show you what that pattern is. Okay. Just a second. So this orbital wave function, if you solve, it has two components. This one I haven't done, so you can copy this down. Psi has two components. That is, psi will write r, that is the radial point of it, and this one is the angular part of it, theta and phi. Theta and phi. So basically, if you consider an axis, only one question they ask on this. I'll show you what kind of question they ask. Suppose we have an electron present somewhere here. This is the point here. So it will have some distance from the nucleus, correct? So this is the distance we have, suppose. This is the radial distance, that is r, this part. Right? And we'll have some angle over here, theta. And when you place the perpendicular line from this, like this way, you'll have some angle with this axis, that is phi. Okay, this is not theta actually. Theta is this side. This side is theta. Right. So this represents the angular position of this electron, theta and phi, and this is radial, the distance from this nucleus. So this part is radial, and this part here is angular. Radial and angular. Okay, this radial part of the wave function. So wave function has two parts, radial and angular. Wave function depends upon the two value, depends on the principal quantum number n and azimuthal quantum number L, n and L. Right. It gives us an idea of size of the orbital. Size, we have an idea of size from this. Angular part is, it is the angular part of wave function, right? And it is represented by L, I'll write down here L, that is azimuthal quantum number. And it depends upon the two value on L and magnetic quantum number M, right? And it gives us an idea of shape of the orbital. Idea of shape. Okay. So that's why from Schrodinger wave equation, we got to know about three different quantum numbers, N, L, and M, right? Not the spin quantum number. Now, what question they ask? They sometimes gives you this relation. They'll write down the wave function this way. That is, suppose I'll write down 420 here. Right? Like this, they'll write down and they'll ask you, which orbital is this? Like this, they ask the question. Okay. This number that you have written here, 4, 2, and 0, this actually in the order of this N, L, and M. So if you see this number, it means if you compare the two, N value is 4, right? L value is 2, and M value is 0. Could you tell me the order with the orbital with this three quantum number? Which orbital is this? Tell me which orbital is this? L value is 2, so it is D. It is not P, Kshitij, right? So it is 4D Z square because M is 0. So this is what you can understand from this particular information. I'll change, Oshik, just a second. Okay, next, yes, the next we have to understand the last concept here of this chapter, that is nodal surface. Very simple, 1, 2, 3 things you have to keep in mind, nothing much. Write down, these are the surface. These are the surface where the probability of finding an electron, these are the surface where the probability of finding an electron is 0, right? That is the nodal surface. Nodal surface, we have two types, okay? One is a spherical node or radial node. Two types. The first one, write down. A spherical node, we also call it as radial node. A spherical node means we have a, yes, nodal surface. It is a surface where the probability of finding an electron is 0. It is a surface where the probability of finding an electron is 0. Correct? Two types we have, a spherical node or radial node. Both are the same thing. A spherical node means what? We'll have a spherical surface where the probability of finding an electron is 0, right? Just you need to memorize the formula we use to find out the spherical node, and the formula is n minus L minus 1. Gives you the number of spherical node, okay? Another type we have, that is non-spherical node. Non-spherical node, we also call it as angular node. Angular node, the formula of this is L. It's non-spherical. We don't represent this on the graph. Okay, there's this formula you should know, and few things I'll tell you what you have to keep in mind quickly here. Okay, so if I ask you what is the total number of nodes, that would be the sum of the two, n minus 1. Okay. Now there is a graphical representation of this nodes, easy one that you have to understand. Okay. I'll show you the graph here. Just a second. All of you copy down this. Could you tell me how many nodes we have in one s orbital? Number of nodes in one s orbital. Tell me. Number of nodes in 1s, number of nodes in 2s, okay? Total number of nodes, if I ask you, the spherical node here, just you need to use the formula. 1 minus L value is 0. This is 0. Angular node is also 0 because it is S subshell. Angular node is 0. So there is no nodal surface for 1s orbital, right? If you talk about 2s, Then the number of spherical node is 1. A spherical node is 2 minus 0 minus 1, that is 1. And the number of angular node is 0 again because it's S subshell. Angular node would be always 0 for S subshell. Now, based on this number of nodes that we have, we can discuss for the graph here. Just a second, I'll show you the graph. Just a second, Pradyun. See, the node is a surface where the probability of finding an electron is 0. Right? It is a surface where the probability of finding an electron is 0. That is what it is. Okay. So you see this graph. I'll explain this graph. 2-3 points you have to understand here. First of all, if they ask you number of nodes, you can find out easily, right, that with this formula that these are the nodes present into this. Now, based on this, we can draw the graph. You see, for 1s orbital, we have the graph of psi and r, psi square and r, and it is psi square 4 pi r square d square. You see this term here. This term is present over here. So psi square, if you remember, it is the probability per unit volume. And if you multiply this with 4 pi r square, which is the surface area, into dr, this term becomes the volume actually. So this integration of this, it represents the probability. So this axis is probability, and this is the distance from the nucleus. Did you understand the the three graphs where we have the axis? This is psi and r, psi square and r, and probability and distance from the nucleus. R is the distance from the nucleus. So these two graphs, we do not have any control because we don't know the relation of psi and r. But this will be a curve here. It won't be a straight line like this. So psi r graph goes like this. Psi square r graph, more steeper curve, goes like this. And psi square r, that is probability versus r graph, it goes up, will have a maximum probability, right? And then comes down. But remember, this graph won't touch the x-axis, otherwise the probability becomes 0, which is not the case of 1s orbital. Did you understand the first three graphs? Just a second, guys. Just a second. I think I have a better picture of it. Let me just cross check. This one. Mm. Oh, I think it got deleted. Deleted me. See this graph only. See, in another class I had drawn this. So, first three graph, did you understand? Or you was there in the last class of quantum number? N is the principal quantum number and L is the azimuthal quantum number. Yes, so before coming for the class, you should must revise once quickly, right? A brief revision is must required. Okay. So did you understand the first three graph? Obviously, you see psi and r relation we do not have. So it is a curve. It goes like this, right? If there is no node, then this graph won't cross the x-axis. It will be above x-axis only. Third graph, did you understand? Third graph is more important. The probability wala graph is more important. Did you understand the third graph? Ansh, did you get it? Now, if you see 2s orbital here, the 2s orbital, we know we have one node here. Means there will be one spherical surface where the probability of finding an electron is 0 or there is no electron present here. Yes, psi square is probability density. That is nothing but probability per unit volume. Okay, so since we have one node here, that's why this graph, you see, it comes down, crosses the x-axis and then goes up. Just convention wise, we'll write this says above this is positive and this is negative. And you see this is psi, wave function. And wave function, I told you already, it can be positive, can be negative, both, right? That's why we have positive, negative both. And this point where it touches the x-axis, then psi is 0 here. Psi is 0 means psi square is 0. Psi square is 0 means probability is 0. And when probability is 0, that point here, it becomes the node. Did you get it? Psi square, you have to just draw the mirror image of this negative part. This negative part becomes positive. Just above this will draw. Remember both the graph here and here, further it won't touch the x-axis. If it touches, it means that point also we have a node, which is not possible because we have only one node here. Right? Then probability graph, if you see, it goes like this. Probability graph always starts from the origin because we know electron cannot present in the nucleus, right? So always in the nucleus here, the probability is 0. So always this graph, you see, it starts from the origin, goes up and then comes down. Now, if you have this kind of graph, because like I said, probability graph is more important. If you have this kind of graph, the peak that you have, the mountain structure that you see here, right? If you have two peak, right, then we'll have one node. That's what I have written here. Number of peak is one more than the number of node. Probability graph always starts with 0, right? The point at which it touches the axis here, there the probability becomes 0 and that becomes the nodal surface. Okay, did you understand this? Yes, all of you got it? No doubt. Please respond. Okay. So you should know the graphical representation, what things we can conclude from the graph. That is one type of question they ask. One type they'll ask you that the number of nodes present. So for that, you just use the formula. You'll find out the number of node. Okay. Another thing that you should know that what are the nodal planes we have for different orbitals, right? It's very simple. You see, if the for 2p orbital we write here, for 2p orbital, number of spherical node is n minus L minus 1, that is 2 minus 1 minus 1, that is 0. There is no spherical node. And the number of angular node, non-spherical, is 1 here, right? So if the orbital is px, for px orbital, we have one angular node, and that nodal plane for this is yz plane, perpendicular one, right? The perpendicular plane is yz plane, and this is the nodal plane for px orbital, right? If you have py orbital, the nodal plane is xz, the perpendicular one is the nodal plane. If you have pz orbital, then the nodal plane is xy plane, and this is the answer here. So you should know what are the nodal planes we have. Similarly, few things you have to memorize. Okay, 3D orbital, you write a copy down this one. I'll go to the next page then. Okay, now if you talk about for 3D orbital, could you tell me how many nodal surface we have for 3D orbital? Spherical node, 2. That's right. Spherical node, is 3 minus 2 minus 1, that is 0. And angular node is 2. Okay, so if it is, you see here, if it is dxy orbital, it is in xy plane. So yz and zx, yz and zx are nodal planes for dxy orbital. If you take dyz, then the nodal plane is xy and y, xy and zx, xy and zx. If you take dxz, the nodal plane is xy and zy. So we have two nodal planes here. One exception we have into this one, right? Write down the note. First you copy down this. Write down dz square has no nodal planes dz square has no nodal plane, but it has nodal surface as cones. Conical shape we have there, right? Nodal surface as cones, C-O-N-E-S. Okay, so this one is an exception. You must remember this. So this is it for nodal surface. Okay, they will sometimes ask you that what is the nodal plane for this one or nodal surface for this one. You should know like this, the perpendicular one is the nodal plane or nodal surface. Now this is the second type of question they ask. Third and the last type here we have, sorry, fourth and the last type we have. One is related with the number of nodes. Other one is the graph types. Third one is this. What are nodal planes we have? And the fourth one is this type of question. I will show you here. The question is, the wave function for 3s electron is given. So wave function is psi. Psi for 3x is given. 3s, not x. Psi for 3s orbital is given is 1 by 81 root 3 pi into 1 by a naught 3 by 2, it's 3 by 2, open bracket, 27 minus 18 r by a naught plus 2 r by a naught square, close bracket, e to the power minus r 3 a naught. A naught is the orbit, the first radius of the first orbit. This is the psi value it is given, relation of psi and r. It says the wave function of 3s electron is given by this, and it has a node at, r is equals to r naught. Find the relation between r naught and a naught. Try this one. What it is? This equation you are saying. Yes, this equation you will get once you solve the Schrodinger wave equation, that Hamiltonian things and all. But that is not there in the syllabus, right? So we don't have to do with this equation anything. You just have to use one condition, and that is it. That's right, Ansh. That is what you need to do. Where is E we have? E we do not have here. R by N. Oh, E is the electron. No, that exponential wala E. E to the power. Answer I'm not sure with. I have to do this. All of you solve this. Anyone? I got one response, Pradyun. Others, what is the answer you are getting? Okay, fine. You can take the help of calculator if you want. Yes, it is a square. That's why it has two values. Okay, fine. I'll do this. I don't know the answer. I'll just have to do this. Okay, see this. it has a node at r is equals to r naught. Node means what? The probability will be 0 of finding an electron. Psi square is 0, and that means psi is 0. So psi for 3s at r is equals to r naught is 0. So we have to substitute this psi is equals to 0 over here and solve this equation. So when you substitute, you will get r naught by a naught plus 2 times r naught by a naught square is equals to 0. That is what you need to solve. So when you solve this quadratic, r naught by a naught is equals to 18 plus minus 4 into 2 into this, that is 216, 4. So could you tell me the answer here? 18 plus minus, this is 324 minus 216. So it is 108 root over by this. Tell me this value. What is the root over of 108? Okay. So it is 10.4 plus minus this. So we have 28.4 by 4 and 7 point, sorry, and 10.4, 18 minus 10.4, that is 7.6 by 4. So that would be 7.1 and 1.9. So R naught is equals to, we get here 0.1 A naught and R naught is equals to 1.9 A naught. Now you see one thing, if you observe here, you'll understand this particular thing very easily. If I ask you the question, how many nodal plane 3s orbital would have? 3s. How many nodal plane for 3s? It is 2, right? Spherical and no angular node, 2 spherical node. Means we should have 2 surface from the nucleus, spherical surface, where the probability of finding an electron is 0. This is one surface, another surface is according to this point, right? 0. And that's why we have 2 value of R naught here. Did you get this? Means at this distance from the nucleus and this distance from the nucleus, we'll have 2 spherical surface where the probability of finding an electron is 0. Yes, that is technically not possible because it is for 3s. It is for 3s, right? Then we should have 2 nodes. Then the equation must be quadratic, correct? Hence, we must get 2 values here. For perfect quadratic you are talking about? No, that won't be the case. You won't get it here. Right. So for those orbitals where the spherical nodes are 3, you will have a cubical equation here. Right. You will have a cubical equation. So one thing also you can observe, they have mentioned this 3s over here. Sometimes what happens, they'll just give you the wave function for an orbital has this relation. They'll give you like this. Then what is the number of nodes we have here? The number of nodes would be the solution of it. Number of nodes would be the solution of it, right? So in that case, if you are getting perfect square, then we'll have only one node there. However, the square is the, the equation is a quadratic equation. But if 3s is mentioned, then you won't get perfect square there. If 4s is mentioned, you won't get perfect square there, right? If they have mentioned 2s, then it is possible to have perfect square. What is x to the power cube minus 1? See, equation, Kshitij, equation, yeah, equation could be anything. It could be anything. You are giving the simplest one. The equation won't be that simple, right? It could be anything, but we should have 3 different values for 3 spherical nodes. Yes, we can have imaginary plane also here. All these are orbitals are also imaginary. It is not like there's a dumbbell kind of thing present within an atom. But if you're talking about imaginary in terms of complex number, then that won't be the case here. You won't get that kind of equation. Okay, understood this? Yeah, so that kind of equation, root over of minus 1, you won't get that. Those kind of equation you won't get. Okay. Right, correct. So these are the 3-4 types of question they ask in for nodal planes. Okay, not that difficult. However, there are many things to understand if you actually want to understand this, but those things are not in our syllabus. So like, you can understand these 3-4 things, how to solve the question, and that is, whenever you get this kind of equation, you have nothing to do, but you need to put psi is equals to 0. That is how we'll proceed in that. So this is it for this particular chapter, that is atomic structure. We have done everything in so detail. So we'll start with the next chapter, and that is periodic classification or periodic properties. See, in this particular chapter, we are going to study about atomic series, periodic table, plus we will also study about the various different terms. Remember, in organic chemistry, GOC, I have used a term electronegativity. Remember that? This one we have only spherical, no angular nodes here. That we cannot say from this one. Right, since we have R value, so we can only get the radial nodes, spherical one. No, we can only get the radial one from this. Okay, so next write down the chapter we are going to start with periodic properties. So I was talking about electronegativity. Remember, we have used the term electronegativity in organic, right? So those kind of terms we are going to see in this chapter. Right. So those kind of terms we are going to understand here in this chapter. Okay, what is the term, what is the application, and other things, correct? So first of all, we'll discuss about the periodic table, right? You must have the understanding of periodic table first, okay, and then we can talk about those terms that we have to discuss, correct? So periodic table, when we got to know about different elements, then we try to arrange those elements in according to their properties, or we can say electronic configuration, or according to their atomic number, atomic mass. So in that way, I'll discuss. In that way, we got different theories that atoms are arranged in this way. Like Frost has given one theory. One, we have Newland octave rules. We have one is Dobrnir triad, Mendeleev's periodic table, and then modern periodic table. Right. So few things are important here. We'll discuss all these theory one by one. So these things are actually similar to the atomic models. That different scientists, they have given their own theory, regarding the distribution of subatomic particles within an atom, and those theory we call it as atomic models. So here also we have different theories of arrangement of atoms. Means how can we arrange an atom in a proper format, in a proper way, right? So that we have different theories we get. Okay. So the first theory that we get is, it is given by the scientist called Frost. Okay, I'll just write down just a second. Okay, so the different theory is given by the different scientists, and this will discuss under the development of periodic table. Periodic table. Okay, all of you write down. The first theory that is given here is, we call it as Prout's hypothesis. Obviously, this was not correct, wrong, and hence we discarded it later. Okay, so what he suggests, that all atoms in the world is made up of hydrogen only. Write down quickly. These things are not important. Even the recent, the syllabus thing, they have changed this thing. This is not given in your syllabus. But for JE, sometimes they ask questions on this, the background of the history of all this. That's why I'm doing this. Okay, so write down all of you. According to this, all elements are made up of hydrogen. Made up of hydrogen, and the atomic weight of any element is given by, atomic weight of any element is n, where n is the number of hydrogen atom present in this. Number of hydrogen atom present. So obviously this was wrong, so we discarded it, right? So this was wrong. The second theory was Dobrnir triad rule. This one is important. You'll get question on this also. Dobrnir triad rule. Dobrnier. All of you write down. write down, he suggested that within a group of three elements, he suggested that within a group of three elements, of similar physical and chemical properties, of similar physical and chemical properties, similar physical and chemical properties, the atomic weight the atomic weight the atomic weight of the middle element the atomic weight of the middle element is the mean of the other two. Example, you see, if you talk about lithium, sodium, and potassium, okay, the atomic weight of lithium is 7, potassium is 39, and the average of these two is 23, and 23 is the atomic weight of sodium. So it is a Daubernier triad. Okay. If you talk about sulfur, selenium, and tellurium, it is 32, sulfur is 32, sulfur is 32, and this one is 128, and the average of the two is 80, selenium is 80. This three forms a Daubernier triad. Okay, chlorine, bromine, iodine, it is 35.5 chlorine, iodine is 127, and the average of the two, you see, if you get here, 54 plus 8, 162.5 divided by 2, the average we are getting 81.25, the average, but the atomic mass of bromine is 80. So it is close actually, not exact value, but it is close and forms a Daubernier triad. Similarly, we can find out for the other elements also. So these kind of elements, Daubernier, he suggested that the elements of physical, chemical, of similar physical and chemical properties forms this kind of triad. Okay, but this also not valid for all the elements. So we discarded this particular thing also. But in the test and question in the book also, you see, they'll ask you this question: which of these groups shows Daubernier triad or follows Daubernier triad rule? Okay, did you copy this? Third theory we have Newland octave rules. Octave rule or octave law. Okay, write down this. According to this theory, write down, according to this theory, if the elements are arranged, if the elements are arranged in order to their increasing atomic weights, if the elements are arranged in order to their increasing atomic weights, every eighth element will have the similar properties every eighth element will have the similar properties to the first one, like the first and eighth note in music. Like the first and eighth note in music. Write it down. I'll just discuss with you. Okay. Again, I'm repeating this. If you arrange in order to their increasing atomic weights, every eighth element will have the similar properties to the first one, like the first and eighth note in music. For example, you see, if we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then again sodium. Magnesium, boron, silicon, phosphorus, sulfur, chlorine, and potassium. See, it is 1, 2, 3, 4, 5, 6, 7, 8. Right, so every eighth element will have the same properties, like we have first and eighth note of music, like sa, re, ga, ma, pa, dha, ni, sa. Right, again you see ni, sa. First and eighth one have the same thing, right? Same note, we have sa and sa. Similarly, the property of lithium and sodium is also very similar. Okay, so this is Newland octave rule, but this is also not found to be correct, and hence we discarded this also. This one and this one. This is the rule we have, correct? Newland octave rule. Copy this down. Hello? Are you there? Okay. Next one, the fourth attempt was made, and this we call it as Lothal-Meyer curve. Lothal-Meyer curve. I'll show you this curve. You don't have to draw this. Okay, just I'll explain few points here. This is Lothal-Meyer curve we have. So this curve is drawn between atomic volume and atomic mass. This is the first thing you should keep in mind. Atomic volume and atomic mass. Then what he observed here, that all the electropositive elements, right, elements of first group, lithium, sodium, potassium, no, rubidium, cesium, all electropositive elements, alkali metals, the first group, occupy the peak of the curve. It present over here. You see this? Lithium, sodium, potassium, rubidium, cesium. This red dot is alkali metals group 1. Okay. The lesser electropositive element, which is the elements of group 2, right? It occupies the descending position of the curve. You see this? Beryllium comes over here. It occupies the descending position. Beryllium, then magnesium, then calcium, strontium, barium. Right? This is alkaline earth metal, group 2. Similarly, non-metals and metalloids are in the bottom of the curve. We have like this, you see, metalloids, cobalt, copper, zinc, non-metals, fluorine, bromine here, right? We have sulfur here, zirconium here, iodine here. All these are on the bottom of the curve. So what he said actually, that on the basis of this curve, what he concluded, right on this point, he proposed that the physical property of the elements, the physical properties of the elements, physical properties of the elements are just a second. Yeah, I'm repeating it. On the basis of this curve, he proposed that the physical properties of the elements are periodic function of their atomic weight. Of their atomic weight. So from this particular thing, we came to know about this fact that physical properties are the function of their atomic weight. Right? Atomic weight. This becomes the basis of the next theory, and that is the Mendeleev periodic table. Okay? Write down, this becomes the basis of Mendeleev periodic table, which is the next theory we have. Atomic weight. You see this? Periodic function of their atomic weight. Okay. This becomes the basis of Mendeleev periodic table. Now, what is Mendeleev periodic table? The modern one that we are using, it is just a modified version of Mendeleev periodic table. Okay. So, write down the heading Mendeleev periodic table. Okay, write down. This periodic table is based upon the fact that physical and chemical properties of an element based upon the fact that physical and chemical properties of an element physical chemical properties of elements are the periodic function of their atomic weight So this table, Mendeleev periodic table, it is based upon the atomic weight, not atomic number. Atomic weight. Right. So basis is the atomic weight. First thing is that. Right. And what he did actually, he was the first scientist who arranged the elements in horizontal and vertical manner, means horizontal rows and vertical columns, right? And this horizontal rows are called periods and the vertical columns are called groups. So according to Mendeleev, that time there were 7 periods, and periods means horizontal rows. And 8 groups. And 8 groups, that is vertical column. Vertical column. Okay, next point you write down. Each group up to 7th, is divided into 2 subgroups A and B. Each group up to 7th is divided into 2 groups A and B. So we have 2 subgroups. So subgroup A is the normal element. Normal element up to 7 it is, right? And subgroup B, it is a transition element. Transition element. Okay, next point. See why these points, the facts are important, because sometimes, especially for Mendeleev, sometimes they'll ask you this question, which statement is correct with respect to the Mendeleev periodic table. So these informations you should have. That's why I'm dictating you this. Next, write down the 8th group was consist of 9 elements. The eighth group was consist of 9 elements. Next one. The elements belongs to same group exhibit similar properties. Right. Elements belongs to the same groups has similar properties. And hence this was the biggest achievement, that the study of elements becomes easier, the properties of the elements, because same group elements have similar properties. That is what that that's what the biggest advantage here. Okay. Mendeleev periodic table, the disadvantage was what? That, write down, the disadvantage is, or drawback you can say, is the position of hydrogen is uncertain. The position of hydrogen is uncertain. It has been placed in 1A and 7A. It has been placed in 1A and 7A group. 7A group. Because of the resemblance with both groups. Okay, so there are many different points we have in this. I have just given you the important one, which you should keep in mind. Okay, all those things you don't have to memorize. Clear? Now, based on this only, like I said, Mendeleev was the first scientist who arranged the atoms in elements in that horizontal and vertical fashion. Okay, rows and column concepts he bring in, right? Based on this only, we have our modern periodic table, that we also call it as modified Mendeleev periodic table or modern periodic table, right? So write down the heading, the last one in this. That is modern periodic table. Which is nothing but modified Mendeleev periodic table. Right? Proposed by Moseley. It is proposed by Moseley based on atomic number. So this is the biggest difference in the two. The previous one was based on atomic mass, and this one is based upon atomic number. What he did actually, he took a metal elements, like metal atom, right? Metal surface he took, and on this metal surface he bombarded high speed electrons on different metal surface. Means with different metal surface, this experiment is done. And what he observed that when it strikes this metal surface, it emits X-ray. Right, from the surface of the metal, it emits X-ray. This is Mosley's experiment. It emits X-rays, and the frequency of this X-ray that is new is found to be directly proportional to the atomic number. It is actually root over of it. Root over of frequency directly proportional to the atomic number, right? And when you write down the relation here, this nu, it becomes root over of nu is equals to A into Z minus B, where this Z is the atomic number. A and B are constant. Just a second, Ansh. Okay, write down A and B are constant here. Are constant. Z is the atomic number. So what happened here? He took a metal surface, different metal surface, and he strikes high speed electron on this metal surface, and he observes that X-rays comes out in this experiment, right? And the frequency of this X-rays, the root over of it, is directly proportional to the atomic number of the metal that we are taking in. We have a graph for this actually. Okay, the graph when he plotted of different frequency with atomic number and root nu, right, into 10 to the power minus 10, you'll get a graph like this. Straight line passes through origin, and hence the relation is. Okay, this is the modern periodic table, that is modified periodic table, right? And this we also call it as the long form of periodic table, right? Long form modern periodic table. Write down few characteristics of this, few properties here. This modern periodic table or long form periodic table based on Mosley's experiment. The experiment I'll show you, right? That experiment that metal surface strikes with the high speed electrons. Based on this experiment, the long form periodic table it gives, it contains 7 periods and 18 groups, vertical columns, and 18 groups the elements belongs to the same group the same group has the same number of electrons belongs to the same group, has the same number of electrons in the valence shell. Okay, so these are the properties we have for long form or modern periodic table. Few facts in this you write down. Write down, bromine is the only non-metal which exists in liquid form. Bromine is the only non-metal which exists in liquid form. Okay, iodine is solid. Iodine is solid. Bromine is the only non-metal exists in liquid form. There are 11 gaseous elements. There are 11 gaseous elements that is hydrogen, nitrogen. You can write down the symbol. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. What all noble gases we have? Tell me. What all noble gases we have? Xenon is Xenon. Okay. Helium, neon, argon, krypton, xenon, radon, right? Plus the 5 elements I told you: hydrogen, nitrogen, oxygen, fluorine, chlorine, and these 6 elements exist in gaseous form. Halogen, the physical state of halogen you must remember, right? I told you fluorine, chlorine are gases, bromine, liquid, and iodine is solid. Okay. Fine. Now we'll must have the understanding of periodic table here, which is very important. So I'll show you the periodic table first. See this. Okay. So you must have the understanding of the entire periodic table. See, this is atomic number 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13, 14, 15, like that. Okay. This group that you have here, the classification of elements you see, This is S block, first and 2. These two are S block. If you see here, we have 10 groups from this point to this point. We have 10 groups here. From this point to this point. And this is D block. D block. This has 6 groups from this point to this point, you see. And this is P block. We know P subshell can have how many electrons maximum? P subshell can have how many electrons? Maximum 6 electrons. So you can have NP1 configuration, NP2, NP3, NP4, NP5, NP6. So since we have 6 different configuration, that's why we have 6 different groups. Could you write down the electronic configuration for boron? 5 electrons. It is 1s2, 2s2, 2p1. See group 13, this one, 3a, 1a, 2a, 3a, 4a, 5a, 6a, 7a, 8a, right? So either you can say in terms of A and B, like we had in Mendeleev periodic table. I told you the groups are divided into 2 categories. One is for normal elements and one is for transition elements. So transition elements are B. You see this? It is 3B, 4B, 5B, 6B. This group is 3B, 4B, 5B, 6B, and so on. This group is 1A, 2A, then it is 3A, 4A, 5A, and so on. Okay. This AA term, if you see here, 3A means there are 3 electrons in the valence shell. Okay. I'm just giving you the idea of it, like what all things you can conclude from this. Suppose we have an element belongs to 7A group. It means in its valence shell, we have 7 electrons. You can check this. I'll show you. I said what? Elements belongs to 7A group. Suppose we have fluorine belongs to 7A. Write down the electronic configuration of fluorine and tell me the electrons in the outermost shell. If you write down, it is 1s2, 2s2, 2p, 5, 9 electrons. You see the outermost shell is not 2p. Outermost shell is second, 2, which contains 2 subshell, S and P. The total number of electrons are 5 plus 2, 7. How many of you understood this? No doubt. Okay. So similarly, if you know the groups 3A, 4A, 5A, 6A, 7A, you can directly say this is the number of electrons in the outermost shell. Like you see, boron is 3A. So it must have 3 electrons in the outermost shell. You see this configuration? 3 electrons. Clear? All of you, please type in CLR if you get it. Tell me fast, quickly. Okay, thank you. Another thing is what? This is one thing that you can conclude. Another thing, when you write down the configuration, 2s2, 2p1, right? So P1 means it is the first group of P block. P2 means it is the second group of P block. P3, third group. P4, fourth group. For example, you see, boron is 2p1, belongs to the first group of P block. This is the first group. For carbon, if you draw, carbon has 6 electrons, right? So in the last, it would be 1s2, 2s2, 2p2. 2p2, the second group of P block. This is 2p3, third group of P block, fourth, fifth, and so on. All the elements you can consider like this. You see, one more thing I'll tell you. P1, P2, P3, P4, you understand? that how only 6 group, why only 6 group we have in P block? Because we have only 6 different P6, correct? Now this is the outermost shell 2 and 2. So this outermost shell represents the period of that particular element. Like you see, boron belongs to what? Second period, you see. This is the second period boron. So this outermost electronic configuration is, the outermost shell represents the period of that element, right? Suppose you have, I'll ask you, what is the outermost electronic configuration of gallium? The outermost electronic configuration of boron is 2s2 2p1. The outermost electronic configuration of carbon is 2s2 2p2. For nitrogen, it is 2s2 2p3, 2s2 2p4, 2s2 2p5, 2s2 2p6. Because all these elements belongs to second period, so their shell should be second only, the outermost shell. With respect to this particular information, if you try to write down the outermost electronic configuration of gallium, right? So this would be, I'll tell you, gallium belongs to which period? Could you tell me? Gallium belongs to which period? Fourth. It is 2, 3, and 4. Since boron has 2s2 2p1, so outermost electronic configuration of gallium would be 4th period, 4s2 4p1. If you want, you can draw. You will get the same configuration, 4s2 4p1. For aluminium, if you write, it is 3s2 3p1. So for the same group, all elements will have similar outermost electronic configuration. Number of period will be changed, but the number of electrons present in the outermost shell, that won't change. It is 2s2 2p1, 3s2 3p1, 4s2 4p1, 5s2 5p1, 6s2 5p1, and so on. Could you tell me this one, what will write? The outermost electronic configuration of silicon. The outermost electronic configuration of silicon. Yes, it is 3s2 3p2 because carbon is 2s2 2p2. So it is 3s2 3p2, 4s2 4p2, 5s2 5p2, and so on. What about this bromine, outermost electronic configuration? Tell me guys, bromine. I want you to respond, all of you, in this. Bromine, outermost electronic configuration. Yes, that's correct. 4s2 4p5. Okay, because fluorine is 2s2 2p5. Fluorine would be 3s2 3p5. Bromine 4s2 4p5. 5s2 5p5. So this is how we can easily understand the outermost electronic configuration of any elements. Okay. Now, another thing you see. This is true for entire periodic table. Here also. What is the outermost electronic configuration of helium? Sorry, hydrogen. Hydrogen, 1s1. Could you tell me for cesium, what would be? What it should be? Cesium, what it should be? 1, 2, 3, 4, 5, 6. First period 1s1, sixth period 6s1, right? So 1s1, it is 2s1, 3s1, 4s1, 5s1, 6s1. Beryllium is 2s2, second period 2s2. This would be strontium. Strontium would be 5s2, 2, 3, 4, 5. So like this, we can have the idea of outermost electronic configuration of any elements. Clear? Tell me. Tell me guys, very important. If you are comfortable with periodic table, it is very easier for you to understand this chapter. And it helps you in entire chemistry. Tell me, did you get it? All of you? Okay. Now the next thing. See, we have classified the elements in blocks. S block, P block, D block. These two are F block. Okay. We classified the elements in block. My question is based on what category? Okay. It is based on the last electron goes into which subshell. If the last electron goes into S subshell, it is S block elements. If the last electron goes into P subshell, it is P block elements. D subshell, D block elements. F subshell, F block elements. Like you see, for these two groups, the last electron goes into S subshell only. So that's why these are S block elements. You can write down the electronic configuration of any elements, you'll get the same thing. Here also you see, for all these elements, if you write down the electronic configuration, the last electron always goes into P subshell, and hence we have P block elements. D subshell, D block elements. Is it clear? Correct. So that's also you can understand in S block, we can have only two possible configurations. One is S1 configuration, other one is S2. That's why we have only two groups here, 1 and 2, S1 and S2. If you talk about D block, so D block can have how many electrons maximum? In D subshell, how many electrons we have maximum? D subshell we have 10 electrons. So the possible configuration is what? D1, D2, D3, D4 till D10. Yes. So we can have 10 groups corresponding to each configuration. So this one is D1, D2, D3, D4, and it goes till here, zinc, that is D10 configuration. Clear? Right. That's why we have two groups here, then we have 10 groups, and then again we have 6 groups. So total 18 groups we have here. Right? 18 groups and 7 periods. Now you have the idea of periodic table, how it is arranged, what all things you can conclude. Did you get the idea of it? Tell me. Yes or no? You have to, yes, I'll do that. You have to just sit with this periodic table. Okay. Google it, take a picture if you do not have book, and then you analyze it. One or two you want, like, once or twice you have to do this. Then you will have the idea of it. Okay. What I said, first of all, I just go one by one in this. The elements are classified in blocks. Why in blocks? Because it depends upon the last electron goes into which subshell. If the last electron goes into S subshell, it is S block, D subshell, so D block, P subshell to P block, F subshell to F block, right? So we have here two S block groups, right? Group 1 and group 2, we have two S block groups. Why? Because we have only two configuration of S possible. One is S1, other one is S2. Finished. Similarly, we have 10 D block groups because D subshell can have 10 electrons. So we can have D1 to D10, 10 different possibilities. Okay. So we have two groups S block, then 10 groups D block, and then 6 group P block. Okay. This is how it is arranged. Extreme left, we have S block elements. Extreme right, we have P block elements. In between the two, we have D block elements. Okay. Now, next thing, that all these groups has one specific outermost configuration. Like if your first group, its outermost configuration is S1. Period can be anything, 1s1, 2s1, 3s1, 4s1, like that. Okay. First group outermost configuration is S1. Second group outermost configuration is S2, and S block is over. If you talk about P block, in P block, the first group that we have, P1 outermost configuration, it is NS2 NP1, then NS2 NP2, NS2 NP3, NS2 NP4, NS2 NP5, NS2 NP6. Okay, if you see these groups and all, right, in terms of A and B, then the number before A and B that is written here, it is the number of electron present in the outermost shell, right? Like 1A, 1 electron in the outermost shell. 2A, 2 electron in the outermost shell. 3A, 3 electron in the outermost shell. 4A, 4 electron in the outermost shell. If you talk about 13, 14, 15, 16, it is simply, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 18. Correct? So this number, if you see group 13, group 14, group 15 elements, if you have this number, just subtract 10 from that, you will get the number of electrons in the valence shell. So basically, let's not make it complex much. Okay, there are so many information I can give you after this also. But a little bit of idea, if you are getting 40% also, it is fine for now, okay? But you have to sit back with the periodic table and you have to think on it, like how the electronic configuration and other thing changes. And this is how the periodic table is. Okay. That's fine. 50-60% is more than enough. But again, you have to revise it before the next class. Okay. In fact, I would suggest that all these periodic table, you must revise the periodic table before every class. Just go through once. Okay. You have a better idea of it. It's very important. Okay. Right. Another thing is what? You see the atom. I'll just write down one simple thing here. What is the atomic number of hydrogen? 1. Atomic number of lithium, 3, then 11, then 19, then 37, and then 55, and then 87. The last one is 87 here. Usually what happens? Yeah, correct. Correct, Ansh. You see in sodium also the last electron goes into S subshell, no? That's why it is S block elements. 3 represents the period. Third period, you see there? Okay. Now, the important thing I would like to mention here is usually what happens, we remember the atomic number of these elements which are there in the top of the periodic table. Yes or no? Would you agree with me? We usually memorize these elements, atomic number, which is there on the top, right? But for exam, you should at least know the atomic number till zinc. That you must remember. If you memorize till krypton, it's fine. But till zinc, you don't have any choice. You have to memorize atomic number till zinc, right? That's one thing. Sometimes if you want to have the atomic number or if you require atomic number of any lower elements, then how do we do that? So for that, we have a certain pattern that you can understand easily. Like you see, for your reference, I have written the atomic number of these elements: 1, 3, 11, 19, 37, 55, and 87. If you look at the difference here, the difference here is, you see, it is 2, then 8, then 8, then 18, then 18, and then 32. The same pattern will follow in all other group except group 18. Group 18 will discuss it separately, let it be. Okay, difference is 2, 8, 8, 18, 18, 32. Okay, I'll write down in the bottom for the first group, group 1. Difference is 2, 8, 8, 18, 18, 32. This is the difference we have. Means what? Suppose you know the atomic number of hydrogen. You add 2, you'll get lithium, 3. You add 8, you'll get sodium, 11. You add 8 again, you'll get potassium, 19. You'll add 18, rubidium, 37. You'll add 18, 55, cesium. Add 32, 87, francium. This pattern is true from here also. Beryllium to magnesium, the gap is 8. Magnesium to calcium, the gap is again 8. Calcium to strontium, it is 18. This is also 18, and this is also 32. Okay. So suppose what is the atomic number of beryllium? Could you tell me? Atomic number of beryllium? Tell me. Atomic number of beryllium, guys. 4, right? So if you do not memorize, suppose magnesium, and suppose beryllium also, if you don't remember, you know the position, right? So hydrogen is 1, helium is 2, lithium is 3, beryllium is 4. Like this also you can do. So once you know this beryllium, you add 8, this is 12. You add 8, it is 20. You add 18, it is 38. You add 18, it is 56. You add 32, it is 88. Did you get the pattern here? Yes, tell me. Did you get the pattern? Respond. Right. So these numbers here, again, listen to me carefully here. These numbers 2, 8, 8, 18, 18, 32, these numbers are called the magic number for group 1. Magic number for group 2, we don't have 2 here, but it is 8, 8, 18, 18, 32. And this is true for all the p block elements except helium. The magic number for group 2, group 13, group 14, group 16, group 17, group 2, group 3, what did I say? Group 2, group 13, group 14, group 15, group 16, group 17. Group 2 and group 13 to group 17, the magic number is 8, 8, 18, 18, 32. Only we have slight change in case of p block elements. This one. Inert gas. Helium is 2, and then it is 10. So we have 8 here. not 2. Here we have 2. Here we do not have 2. 2, 8, and then 18. Krypton is 36, and then it is 54, and then it is 86. So gap, if you see here, it is 8, it is 8, it is 18, it is 18, and it is 32. Right, it's 8, 8, 18, 18, 32. See here, 8, 8, 18, 18, 32. So it is same for this also. For this also you can consider. The position is this 1s1, 1s2, but still this gap is not 2 here. Okay. So this kind of pattern you must analyze, you must remember. This helps you in finding out the atomic number of any element in the exam if you forget. I would suggest in market or in Amazon, any other merchant you see, you can buy a very large size periodic table, do all these all these stubble everything over there, and you can stick this onto your wall, right? Wherever you study, or wherever you sleep, wherever you usually spend your time in the house, there in the wall you can paste, you can stick it, so that if you just go through it once, if you just look at it once in a day, you will have this in your mind. In the exam, you could easily visualize the periodic table, the entire periodic table. That helps you a lot. Did you get it? Yes. No doubt in this? Okay. So I guess you all have understood what is how the elements have been classified in the blocks. What is the reason for that? Okay, and what are the different blocks we have? Electronic configuration, you got the idea. Okay, now there are various terms that we use, right? Different types of elements we have in this. That will start after the break. Okay, normal, representative elements, typical elements, okay, bridge elements, diagonal relationship. All these we'll see after the break, correct? So take a break now. We'll resume the session at 6:45. Okay. Yeah. 6:45 will resume. Take a break now, guys. Okay, hello guys there. Okay, so so there are various classification of elements we have that you write down. Classification of elements. The first type we have here is normal or representative elements. Normal or representative elements. Write down. These are the elements belongs to. These are the elements belongs to S or P block. These are the elements belongs to S or P block except noble gas. All elements belongs to S and P block except the noble gas. Normal or representative elements. Second one, typical element. Write down. These are the elements These are the elements which shows the property of these are the elements which shows the property of properties of other elements properties of other elements belongs to the same group. These are the elements which shows the property of all other elements belongs to the same group. So typical elements are elements of third group. These are the elements of third group, not the second one. Elements of group 3, third group. Like we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, etc. Sodium, magnesium, aluminium, all third group elements you can consider. Okay. Sorry, third period. I'm sorry, my bad. Third period, yeah. Okay, third period. Okay, so elements of third period represents the property of the other elements belongs to the same group. Like sodium represents the property of alkali metals, first group, right? Phosphorus represents the property of the nitrogen family, right? That group, this thing here. Next, write down bridge elements. Bridge elements, write down. Typical elements are the elements which represents the property of the other elements belongs to the same group. Other elements belongs to the same group, not period here, right? Belongs to the same group. Examples are the elements of third period. Examples, elements of third period, like we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, etc. The third one, we have bridge elements. Write down the elements which act as a bridge. The elements which act as a bridge between two different group elements. Okay, the elements which act as a bridge between the two different group elements are called bridge elements. For example, you see, if you talk about sodium, magnesium, and copper, sodium belongs to 1A group. This belongs to 2B group. Roman we should write. This is 1A, this is 2B group, and magnesium present in between these two. So this is the bridge elements. Just definition you have to keep in mind. Another example is potassium you take, calcium you take, and silver. So potassium is again 1A, silver is 2B, and calcium present in between the two. So it is a bridge element of the two. Okay. Okay, the next one is the diagonal relationship. Diagonal relationship. Write down some elements belongs to second period, some elements belongs to second period shows similar behavior with the elements of third period okay, again I'm repeating, some elements belongs to second period shows similar relation with the elements of third period which are present diagonally opposite to them, which are present diagonally opposite to them are called, diagonally opposite to them are said to have diagonal relationship. Again, I am repeating this. Some elements belongs to second period shows relationship with or shows similar behavior with the elements of third period which are present diagonally opposite to them are said to have diagonal relationship. Right, this one is important. Like you see, if you look at the position here, we have lithium, sodium, beryllium, magnesium, then we have boron, aluminium, calcium, silicon. So left to right, you have to go diagonally. Like you see this one, this one, this one, this one. Okay. So these two elements are observed to have similar properties. What all properties we'll discuss later in this chapter. But these elements are said to have similar properties, and this we call it as diagonal relationship because the elements are present diagonally to each other. Like this we don't define. Okay, left to right we go. That is a diagonal relationship. Okay. Fifth point. Transition element. Transition element. These are the D block elements these are the D block elements which has unpaired D electron these are the D block elements which has unpaired D electron okay, which has unpaired D electrons in their ground state or excited state, right? These are the D block elements which has unpaired D electrons in their ground state or excited state. Like for example, you see, if you take an example of scandium, okay, or titanium. Titanium, could you write down the electronic configuration of this? All of you, please. That's what I want you to identify it. What is the position of titanium? No, it's not. Titanium is after scandium. Yeah, it's 22. That's right. Titanium atomic number is 22. Now you write down the electronic configuration. And I want you to write down the electronic configuration of zinc also. We have discussed it. Three S2, 3p6, 4s2, 3d2. Okay, correct. What about zinc? Yes. So the electronic configuration here is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Okay. For zinc, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. In short, in terms of argon also we can write. Okay. This 3d electron you see, 3d has 5 orbitals. 1, 2, 3, 4, and 5. And it has 2 electrons present according to Hundsrud. And this has all the 5 orbitals filled, completely filled, right? So transition element, the definition is what? D block elements which has unpaired d electron in their ground state or excited state, right? You see in zinc, all d electrons, we are talking about d electrons here, this electrons and this electrons. In zinc, these electrons are paired, right? This one is not paired. Okay. So this one is this one is titanium. It has unpaired d electron. So this is the typical element. Sorry, not typical, transition element. This is the transition element, right? This zinc is not transition element, it is D block element. So transition element comes under D block only. Okay, so this is the difference between the two, right? You must keep that in mind. The D block elements right, which has unpaired d electrons are called transition element. Which one, Oro? Hans rule, you know, Oro? Could you think of Hans rule over here? Okay, understood, no? Because of Hans rule only, it will, the pairing is not possible until all the electrons are, unless all the electrons are singly occupied, no? No. After 3D6 also it is transition. 3D7 also it is transition. Whenever you have unpaired d electron, it is transition. Except 3D10, yes. Right. So all transition elements are d block elements, but all d block elements are not transition elements. The vice versa is not true. Right. Transition elements are d block, but d block are not transition elements. Okay. So we have zinc, CD, and Hg. For these three elements, the d orbitals are fully occupied. D10 configuration it has. That's why these three are d block elements. All other elements are transition. Right. See, one more thing I'll just show you here. Zinc, you know the configuration this. CdHg, you see zinc, cadmium, and Hg. These elements belongs to the same group. I'll show you. You see this. Zinc, cadmium, Hg. So if it is D10, this one is also D10. This one is also D10. So this is the one that I have written. The Zn, Cd, and Hg are D block elements, not transition elements. This is the application of the pattern that we learned few minutes back, half an hour back. Okay. If this has D10 configuration, this also has D10 configuration. This also has D10 configuration. Hence, since they belong to the same group. That's why these are D block elements, not transition elements. Did you understand this point? Yes. So all of you write down, all transition elements are D block elements, but vice versa is not true. Right? Next, write down inner transition elements. Inner transition elements are F block elements. That is it. Inner transition elements are F block elements. Write down inner transition elements. Inner transition elements are F block elements. F block elements, we have two series in this. Two series. The first one is we have 4F series. 4F series means the electron goes into 4F subshell. Right, 4F series, it starts with cerium, atomic number 58, and goes up to lutetium, lutetium, atomic number 71. Okay, this has 14 elements because F can have 14 electrons. So this series has 14 elements, right? And this cerium lutetium, this we call it as lanthanide series. Lanthanide series. Okay. The second series we have, that is 5F series. 5F series. It starts with thorium, TH, atomic number 90, and goes up to lawrencium, atomic number 103. This also has 14 elements. Right? And this we call it as actinide series. Actinides and lanthanides. Remember always, lanthanide starts with cerium 58, goes up to lutetium 71. Actinides starts with thorium, goes up to lawrencium 103. Did you copy this? Yes, tell me. Okay. Now you see, I'll show you in the periodic table. I'll take the new one because again, see this, I'll show you here. Okay, you see here. This is barium. I'll write down here so that you can understand. This is barium and its atomic number is 56. Then this is 57. And this 57 is lanthanum. It is 57 is lanthanum. After 57, the atomic number should be, if you see here, it is 37, 38, 39, 40, 41, like this it goes. 37, 38, 39, 40, 41, like this it goes. But here it is 55, 56, 57, but this one is 72. After 57, we have 72. Similarly, this one is 87, this one is 88, this one is 89, but here we have 104. So 40 elements, there's a gap here. 14 elements, not 40, 14 elements, there's a gap here. These 14 elements, it is shown over here. You see, this is 57, this is lanthanum. 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 This one is actinum. 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 Right? This one is cerium. This is atomic number 58, you see. This is cerium, atomic number 58. And this is lutetium, atomic number 71. So what happens after this lanthanum? The electron starts fill into 4f orbital. If you look at the electronic configuration for this one, F subshell, this one is 4f1, 4f2, 4f3, 4f4 till 4f14. right? So from cerium to lutetium, this series we call it as lanthanum series or lanthanides because it starts after lanthanum. That's why it is lanthanides. So it is always, students are confused in this one that lanthanides starts with lanthanum. No, lanthanum is not a part of lanthanide series. Okay, since lanthanide starts with cerium because the F subshell has one electron here, it starts filling here, right? That's why the series F series starts from cerium to lutetium. That's why the lanthanide series starts with cerium and goes up to lutetium. If you talk about 4F series, this is the same thing. It is actinum, starts after actinum. This is 90 and this is 103 and this is 5F series. Okay, so this one is actinides, this one is lanthanides. They don't ask any question on this. Just you should know what is the first element and last element for the two series, lanthanides and actinides. Clear? Okay, so I want you to do some, revision work on this periodic table. Whatever I have discussed today, right? You must revise this. If you have the periodic table with you, fine. Otherwise, you can easily get it online. Okay, Google it, you will get the periodic table, open it, and then you can check. Okay, all these things, very important. If you have a better understanding of periodic table, it's very easy for you to understand this particular chapter. It helps actually in entire chemistry, but especially in this chapter, it will be very comfortable. Okay, so this is the few properties we have discussed for, initial properties we have discussed. Now, for a given elements, how do we predict the period, group and block for that particular element? How do we predict the period, group and block? Write down the prediction of period, group and block. Right. Usually what happens, electronic configuration will be given in the question. Is given. Now, in this what happens, the period is the maximum value of n. You can easily find out period for any elements. In the electronic configuration, maximum value you check, that is the period. Okay. Subshell, that is block. Subshell means SPDF, right? Subshell or block B is the subshell which takes the last electron. That's what we have discussed. No? S block, P block, D block. The last electron enters into S subshell, it is S block. So it is the last electron. Group, we have certain formula here. For S block, write down. Group, you have to find out. This too is done. For S block, the formula is, if the configuration is this, inert gas configuration, and NS1 like this, it means it is group 1. Any doubt in this? If you have inert gas configuration and it is NS2, then it is group S block, we can find out this. For P block, what we do? For P block, we'll write the group is equals to 12 plus number of electrons in P subshell. In P subshell, outermost P subshell. Okay, we can write down this 12 plus number of electron in P subshell. Why 12? Because you see, if it is 3p1, right? So 3p1 is this one, 3s2 3p1 is aluminium. So we have 10 electrons here plus 2. So this 10 plus 2, 12 you have to add. Means in this 3p1, 1 plus this 12, then it comes to be 30. That's why we have that formula. 12 plus number of electrons in outermost P subshell. We'll do some example, you will get it. If it is D block, then group will find out group is equals to 2 plus number of electrons in n minus 1 D subshell. N minus 1, right? Penultimate shell. N minus 1 is D subshell. Not the last one, right? Suppose if you write down 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, right? So here the outermost shell is 4s, not 3d. Electron goes into 3d orbital after 4s because of its energy, but outermost shell is fourth shell. So outermost shell is fourth. This is n. So n minus 1 is what? 3. So 1 electron we have to consider here. Okay. This is what it means. Number of electron in n minus 1th D subshell. If it is F block, write down this. If it is F block, for F block, the group is always 3. Always 3. Because you see this again periodic table. This is the F block, right? And F block is present here. You see this present here. This is fourth one, and this is third group we have here. F block, third group. So F block is, you don't have to do anything. If it is F block, the group is always 3. Copy this down. Done. Okay, look at this example. One S2, 2s2, 2p6, 3s2, 3p6. You need to find out the period. Then we have block, and then we have group. One S2, 2s2, 2p1. XE, 4f0, 5d0, 6s2. Krypton 4d10, 5s2. Argon 4s2, 3d6. Find out the period, block, and group. See, in the first one, the period is the maximum value of n, that is 3. You won't have any confusion in this period, right? 3. Last electron goes into p subshell, the block is p. And for p block, we know the formula. It is 12 plus the number of electron in p. The group is 18th group here. Any doubt in this? Tell me. Yes, guys, please respond. Okay. This one, the period is 2. The block is p. And it is 12 plus 1. That is 13 group. Boron. This one is maximum value of n. Period is 6. Block is s. And if it is s block, ns2 configuration we have. So it is group 2. Right? Period is 5. Block is s. Is it s block? It is d block because electron goes here. It is like 4s2 and 3d. Like 4s first and then 3d. I have written it this way, but first electron goes into 5s and then it goes into 4s. Energy also, if you see, the 5s energy is 5 n plus l value, and this one is 7, right? This has more energy, fills later, right? So it is 5, block is d, and for d block we have the formula that 2 plus number of electron in n minus 1th d subshell, that is 10. N is this, n minus 1 is 4, 10, so 2 plus 10, that is 12. This one, again the same thing, right? So this is 4, d, 2 plus 6, that is 8, 8th group. Did you understand this? Guys, respond. Any doubt? All these questions you can easily do if you have a better understanding of this periodic table. Right, you can easily use that, but actually the formula, if you memorize, you can save your time in the exam. That's why the formula is given. Okay. Fine, guys. Thank you. So we will continue from this next class. Okay, we'll see some more properties next class. Okay. Yeah. Take care, guys. Yeah. Thank you. Bye.